When we look at a linear system problem, the data to that kind of problem is a matrix A and a right-hand side vector B, and the solution to the problem is a vector X. So if we're going to talk about the conditioning of these problems, we have to talk about what it means to have a small perturbation, or to measure the size of a perturbation to vectors and matrices. And that's the idea of what we call a norm. So we're going to start with this video with vector norms. There are all kinds of ways you can define vector norms, but there are three that are the most commonly used. So we're going to define these as though the vectors could have complex entries, because we're going to need those eventually, and they're not much more difficult than the real number case. So the first of these norms is the 2 norm. Okay, so we use the subscript 2 with the double bars to take the 2 norm of a vector, and it's the square root of the sum of squares of the elements, and those squares are in absolute values. So if it's a complex number, remember that the magnitude or the absolute value of a complex number is itself the square root of something. So if we square that, the magnitude of a plus ib squared is a squared plus b squared. So that's what we would put into this formula here. A simpler way of writing this formula is as the square root of x star x. So x star, you may recall, stands for the conjugate transpose, or the Hermitian, of a matrix or a vector. And it's the complex conjugate transpose. Okay, so for a real entried vector, x star is the same thing as x transpose. And so it's the square root of the dot product of x with itself, if you want to think of it that way. So sometimes we call the 2 norm the Euclidean norm, because it's the same as Pythagoras' theorem in 2 dimensions tells us is the length of a vector in the Euclidean sense. Another popular norm is the 1 norm of a vector. That's the sum of the absolute values of the entries. Again, that absolute value for the complex case is defined as up above. And then the third choice that we might use a lot is the infinity norm, also called the max norm. It's just the largest element, again, in absolute values or complex magnitude. So for example, here's a real case. If we have the vector x is 3, 4, 1, 2, then the 2 norm of x is the square root of 9 plus 16 plus 1 plus 4, which is the square root of 30. The 1 norm of this vector is 3 plus 4 plus 1 plus 2, so it's 10. And the infinity norm of this vector is just 4, the largest element in magnitude. Now all these norms, and any other norm that you might try to define, has several key properties. So first of all, if we multiply x by a scalar, then that multiplies the norm by the absolute value of the scalar. And that's why we call these scalars. They scale the length of a vector. Second property is that the norm of any vector is greater than 0 if the vector is non-zero. And I guess I should add that the norm of the 0 vector is itself equal to 0. And finally, we have an inequality on the sum of 2 vectors. This is called the triangle inequality, because it's another expression of the fact that the shortest distance between 2 points is a straight line. So those 3 properties we can count on with our norms. Now, one of the things that's interesting to do is to use the norms to visualize what we would call a circle. So in any norm, we would say the unit circle is the set of vectors that have norm equal to 1. Well, in the 2 norm, that corresponds to the usual sense of distance, and so it corresponds to the usual sense of a circle. So it's a circle whose center is at the origin with a radius of 1. Okay, so that would be the 2 norm. Now in the 1 norm, what we're saying is that the sum of the absolute value of x1 plus the absolute value of x2 is equal to 1. As you know, with absolute values, each one corresponds to a plus or minus. So we would have plus or minus x1 plus or minus x2 is equal to 1. Well, that gives you 4 possibilities. There's 2 choices of the first sign and 2 choices of the second sign. If you write them out, each of those possibilities is a straight line with angle positive or negative 45 degrees. And when you work out what it all means, you get this set, which is a square turned on its edge. So that would be considered a circle in the 1 norm. And then finally, in the infinity norm, we have that the maximum coordinate value is equal to 1. So that means at least one of the coordinates has to be on the lines plus or minus 1. So we have 3 different unit circles depending on the norm that we choose. Another way of thinking about norms is measuring distance. So if you have any 2 vectors x and y, the norm of x minus y is what we would term to be the distance between those 2 vectors. And using that sense of distance, right, if the distance between a sequence of vectors and some value goes to 0, okay, then we say that the sequence of vectors converges. So now we have a way of talking about sequences of vectors and their convergence to a limit. One more theoretical bit that comes in handy sometimes in more advanced work is there's a theorem known as the norm equivalence, which says that if you have any 2 vector norms, there's a way to bound one of them in terms of the other from above and below, just using constants that don't depend on the vector x at all. The main significance of that result is that you can use it to prove the following corollary, that if you have a sequence that converges in one particular vector norm, then that sequence actually converges in every norm. And one of the interesting things, or one of the things that makes that particular result so useful, is that if we look at the infinity norm, okay, so if we know we have convergence in any norm, then we have convergence in the infinity norm. I'm sorry, this is xk and this should be x star, right? So that means that the maximum over all entries, the maximum difference over all entries also goes to 0. And that can only happen if the sequence converges entry-wise. So in other words, a sequence of vectors converging, no matter what norm we use to prove it, means that all the elements of that vector converge to the elements of the limit vector, which is just what you would expect, but it's nice to have a mathematical proof of the fact too.